Other way to control, to fight corrosion is by material selection. So what is the application is the first question, or one of the first questions that we need to answer. We need to know, when we describe the coating types, we need to know the temperature, we need to know the environment in which will be exposed. What is the function? What will there be a stress present? There will be stress, it will be bends, it will be loads. Is stress corrosion cracking a possibility? Stress corrosion cracking is very important to always consider because stress corrosion cracking counts for stresses, for material susceptibility, and for corrosion. So we need to look for these three elements when we evaluate stress corrosion cracking. And then what is the desired service life? Usually it's 20-25 years of service, but some materials, they are outstanding and they can be utilized for 30-45. It depends the design and it depends the needs and requirements from the utilization. We need to also include the previous experience. It's any similar situation. What is the plant corrosion test, laboratory testing, pilot plant experience, research experience? Everything needs to be in common when we decide to use a different material to protect against corrosion. How corrosive is the environment? Is it sour, sweet, oxygen? How's the temperature? Is acid, is basic? What is the flow rate? It's an erosion problem. It should be agitation, cavitation. How's the pressure? Pressure drops, gas formation. All these things needs to be evaluated, needs to be very well understood what is the performance of the materials. The typical material when we are trying to upgrade steel to something better, we need to look first, the first ones is the 300 series, which is basically the austenitic stainless steel. Definitely it improves uniform corrosion, it's stainless steel. However, suffers from chloride attack when the temperature is higher than 60%. It's very important if you decide in some point in your career to use stainless steel, you need to ensure that the flow inside is moving constantly, because otherwise chloride attack will take place and will basically destroy your passive film on the austenitic stainless steel. It can have problems of sensitization, which is basically when the temperature change, they can lose the chromium along the surface, and then you lost the passivity layer, and it could be susceptible to stress corrosion cracking and crevice. So crevice corrosion, I will explain what crevice means, but it's basically this passive layer is break, and then it allows the corrosive elements to corrode the steel there. There is another that is the 400 series, that is the ferritic. It's better to protect against stress corrosion cracking. It's very easy or easier to weld. It's not very easy, but it's easier to weld than the austenitic. And it's usually the one when we upgrade to high temperature corrosion. It could be a duplex mixture of austenitic and ferritic, and it's very good for corrosion resistance. Usually the labs that they are using environments of high pressure and high temperature or autoclaves, they are sometimes, most of the time, use a duplex stainless steel to do the lab testing. It could be even aluminum alloys. So we discussed sometimes, and then this is the alloy, like 500 magnesium and 7,000 copper. 5,000 magnesium and 7,000 copper. Why? So the copper the aluminum is very flexible, it's very malleable, so we can use it. The magnesium adds some properties of stiffness, and the copper also helps in the corrosion resistance. It's very good in neutral pH. However, pH is amphoteric type of material. Aluminum is amphoteric type of material, means that it corrodes at low pH and it also corrodes at high pH. It suffers from localized corrosion. That's true because aluminum tends to have this passive layer of alumina or aluminum oxide, which is very resistant, but it could be break, and then it tends to have localized corrosion. And they have the exfoliation problems basically because aluminum is ductile, and then it could be easily removed. Nickel is one of the most expensive and hast alloy, and it's very well known when you have research, and that basically everything is done by hast alloy or duplex stainless steel. Hast alloy is one type Inconel is another, Monel is another, and those are very good for corrosion resistance in almost all conditions. It's very expensive, and the joint by welding is very difficult. 9 chromium, low alloy chromium, is basically you enrich the steel, your base steel, with chromium to form the chromium oxide. You don't go to the stainless steel, but you improve your corrosion resistance, of course, by CO2 corrosion. H2S corrosion is very good. However, it's been proved that chromium adding in low concentrations, just like these concentrations, reduce the performance of corrosion inhibition. And well, at the end, copper alloys, good atmospheric marine corrosion resistance, not good for H2S environment. Copper alloys, if you go onshore, that's probably some materials that you will find for copper, because it's very good for atmospheric corrosion.